So K value, it is 981 Newton per meter. Okay, so that we have calculated by experiment procedure. And the mass that we have attached to the spring is 4 kg. So this is 4 kg and this is 981 Newton per meter. Now we will allow this mass to oscillate longitudinally by giving some initial displacement x. Okay, and then we will find out its time period and then its natural frequency by using this formula. Omega n, it is equal to 2 pi upon t. Okay, and we will compare this experimental value. So this is the experimental reading with the theoretical value. So theoretical natural frequency, which is square root k upon m. So this is square root. So k is 981 and the mass is 4 kg. So this value, so this is 15.66 radian per second. Okay. So just you can repeat this experiment if we are conducting it in the laboratory. Okay, just to minimize the measurement error. So we should measure 10 oscillations and then find out the time period t upon 10. So now here we will directly get the time period as we are conducting experiment in the software. Okay, so directly we will get one waveform. So as this mass is oscillating, so software, it gives the waveform, which is displacement versus time. Okay, so here this is the x and this is the time axis. So if you measure any two peak to peak distance, that is the time gap between these peak to peak values, so it will give directly time period value. So we have selected this as a T1 and this is the T2. Okay, so this is your capital T, that is the time period. So T is equal to T2 minus T1. Okay, so you can observe here in the simulation. So up to 3 seconds, if you observe in the graph, we give some initial displacement. That means we apply the force till 3 seconds. After 3 seconds, we remove that force. So there is no external force on the spring mass system. And then system will oscillate because of the spring force and the inertia force. So this is the free oscillation. So as there is no damping in the system, the mass will keep oscillating with the same amplitude for the infinite time. Now from this graph, we will find out the time period. So just observe these peak to peak values. So this is 3.4 and this is 3.81. Okay, so take the difference, 3.81 minus 3.4. So this value is 0.41. Okay, so 0.41 is the time period. So you take this screenshot for this waveform. You have to add this screenshot in your experiment writer. So the time period that we have got, this is 0.41 second. Okay. So just you can multiply this. So this is 4.1 second. It is a time for 10 oscillations. Okay. So it will remain same 4.1. This is 4.1, 0.41 and 0.40. So we will not repeat the experiment. So now calculate the omega n, which is a 2 pi upon t. So this time omega n, sorry, frequency. So it is 15.31 radian per second. Okay, so it is the same value. So experimentally, omega n value, it is 15.31 radian per second. Okay, so both the values are nearly same. This is 15.31 and 15.66. Okay, so in this way, you can find out the natural frequency of any spring mass system by experimental procedure and by theoretical formula, which is square root k upon n. Okay. So now we will conduct the experiment for the parallel arrangement of the spring. So for this parallel arrangement, so you can take the screenshot. You have to draw the diagram in your writer. So this is K. So K value, this is 200 Newton meter. So here the stiffness of the spring is known, which is a 200 Newton meter. The mass attached, this is 4 kg. Okay, so its schematic representation. So this is the schematic parallel spring system. So theoretically, if you want to find out the frequency of this system, then we should convert two spring into its equivalent single spring. So its equivalent system will be, so this is the K equivalent for the parallel arrangement. Okay. So what is the formula for K equivalent? For parallel system, K equivalent is equal to K1 plus K2. So both the constants, it is a K only. So it is a 2K. So that is equal to 400 Newton per meter. And theoretical value for the natural frequency is omega n square root K equivalent upon m. So that is equal to square root K equivalent is 400 and mass is 4. So it is square root. So this is 5 radian per second. Okay. So this is the theoretical value. Now we have to find out the natural frequency experimentally. That means we have to oscillate the mass, then we will measure the time period, and from that time period we will find out the frequency. So here you can observe how the mass will oscillate, and from its waveform, that is the displacement versus time, we will measure the time period. So this is the initial displacement, and this is the free oscillation. So again, observe this waveform and this oscillation. So at 3 seconds, we remove the force, and then mass oscillate freely. Okay, so here we will measure the time period. So you should measure peak to peak distance. So this is 3.63. You note down this value. So this is a T1 value. You can take the screenshot, and 4.26. So here the time period is 0.63 seconds. So for the parallel arrangement, you have to draw the same observation table. That is the serial number, time for 10 oscillation. So this is a small t, capital T, that is a time period. It is a small t upon 10, and omega n, this is equal to 2 pi upon t. So the time period is 0.63. So you can take this value as a 6.3 time for 10 oscillation. And omega n experimentally, this is a 2 pi upon t. So check this value. Okay, just correct this. So this is 400 by 4, this is 100. So this is a 10. And this value, it is 9.96. Okay. So omega n experimental for the parallel arrangement, this is equal to 9.96 rad per second. And omega n theoretical, this is 10 rad per second. Okay. So both the values are same. And the next is the series arrangement. So for the series arrangement, so this is the first spring with constant K. This is the second spring, and this is the mass connected. Okay. So this system we will convert into equivalent simple spring mass system so that we can find out the theoretical value. So this is a K equivalent. Okay. So for the series arrangement, we have the equation K equivalent is equal to 1 upon K1 plus 1 upon K2. Okay. So here K1 is equal to K2 is equal to K, that is equal to 200 Newton per meter. So we have selected the same spring having the constant 200 Newton per meter. So this value will be 1 upon 200 plus 1 upon 200. Okay. So this will become 400 upon, this is 4 into 10 to the power 4. This is 1 upon K equivalent. And this, take the inverse. So it will become 4 10 to the power 4 upon 4 10 to the power 2. Okay. So this is 100. So this is 100 Newton per meter. So this stiffness is 100 Newton per meter for the series arrangement. And mass is 4 kg. So theoretical value for the series arrangement, omega n, which is a square root K equivalent upon m. This is square root 100 upon 4. So this is 25, and that is 5 rad per second. Okay. Now we should check this value by experimental procedure. Okay, so this is the series arrangement. So here you can observe two springs, they are connected in the series at this point. Okay, so now observe the oscillation. So this is the initial displacement up to 3 seconds. After 3 seconds, mass will oscillate freely. Okay, so from this waveform, we will find out the time period for this series arrangement. So note down this first value. This is 4.28. And second is 5.54. So this is 1.26 is the time period. So this time period for the series arrangement, it is 1.26 seconds. Okay. So omega n experimental value, this is equal to 2 pi upon 1.26. So the answer is 4.98 radian per second. Okay. So in this way, you can verify the theoretical formula by experimental procedure. Also, you can verify this formula that we are using to calculate the equivalent stiffness. So as each spring is having the constant 200 Newton meter, okay, and by this formula we find out the equivalent value, which is 100 Newton meter. Okay. So experimentally, suppose if you want to find out the equivalent value of the stiffness, then you should connect two springs in this series arrangement like this. Okay. And then attach one known weight and then measure the static deformation. So let us take this is a static deformation. So it is a delta. Okay. So the formula is spring force is equal to, so these two spring, they will have equivalent value as a K equivalent. Okay. So this is K equivalent into delta. So we know the value of delta. So K equivalent is equal to force upon delta, and force is nothing but this mass into 9.81. So it is a mg upon delta. Okay. So experimentally, if you want to find out this equivalent value, then we should measure the deformation or displacement of the mass. Okay. And then by using this formula, you can find out the K equivalent. So let us check whether we get the same value as 100 Newton meter. Okay, so now here I have changed the weight to measure the equivalent stiffness. So I have connected here 2 kg. So it is 2 into 9.81. So it is approximately 20 Newton. Okay. So for this 20 Newton, we should measure what is the deformation. So right now, so this is at 38 centimeter. Okay. So due to 20 Newton, what is the deformation? Okay, so here you can observe the initial position or undeformed length for the spring. So this is 37.9 millimeter. Okay, so you take this first value as a L1, 37.9. So 37.9, it is in centimeter. Then after applying 20 Newton force, so we get the deformation as this is 59, then this is 59.5. Okay, so 59.55, you can take half. So 37.9 minus 55.55 millimeter, sorry, centimeter. Sorry, 59.55. So 37.9 minus 59.55 centimeter. So you will get the answer as 21.65. Okay, so 21.65 is the deformation. So this is the series arrangement. So we have connected 2 kg mass, so approximately is 20 Newton. So because of this 20 Newton force, so this is 20 Newton force. So there is a deformation. So this deformation, this is 21.65 centimeter. Okay. So K is equal to, that is a K equivalent for both the springs. So this is force upon static deformation. So force is 20 Newton and the static deformation is 21.65 10 raised to minus 2. So this is in Newton and this is meter. Okay, so check this value.